Hello, everyone. I'd like to welcome you to our webinar. We're going to wait just a few more minutes for people to show up, and then we will get started.
Danke sehr, Krieg. Oder Latina. Sí, ausgekist. Eine Hennekist.
All right, so we're going to go ahead and get started. Again, welcome to our webinar. We will be talking about an alloy we've created called REL61. That is a cost-effective alternative to SAC305 with enhanced performance. So I am your speaker today. My name is Gail Towle. I'm a content specialist for AIM Solder. I have a background in math and physics. I used to work in higher education, done a lot of technical writing, and I give webinars for AIM, among many other things. And I hope that this is informative for everyone who's here. So just a brief summary, AIM offers a lot of technical support services. So anyone who's interested in more details about that can visit our website after the webinar, but we do solder joint analysis, stencil design support, solder analysis, reclamation, consulting, and technical trainings as well. So on to the main show, REL61. So REL61 is a lead-free alloy, and I want to start by sort of telling you where it fits with other lead-free alloys. So when the industry started going lead-free, the first generation alloy that everyone's probably most familiar with is SAC305 that came on the scene. It was compatible with existing processes. It was also compatible with lead components. It was higher in cost. It does have several drawbacks, not as good mechanical performance and aging performance compared to tin lead, and then also compared to some later generation alloys that have come on the scene. Second generation lead-free alloys were sort of variations on SAC, so the tin, silver, copper, varying the amount of silver content to lower the costs. still compatible with lead. Some reduced defects with SN100C, which was a primarily tin alloy with some additives. But still some drawbacks to some of those. Third generation alloys have now come on the scene. REL61 falls into that category. So REL61 is a low silver alloy, so it tends to be lower in cost than SAC305. It does have some bismuth added, and the small percentage of bismuth actually tends to improve a lot of the mechanical properties. It also slightly lowers the melting point, improves the aging performance quite a bit. The only drawback being that bismuth containing alloys tend to not be compatible with lead. So if there's still lead in the process, what happens is bismuth can combine with lead to form a very low melting eutectic, which can cause some structural issues with a joint. But there's other third generation alloys, including we also have a REL22 alloy, which is our high reliability alloy meant to compete with the mechanical performance of tin lead. REL61 sort of sits in the space of being similar in performance to SAC305, SN100C. It performs slightly better across some of those metrics, but it is much lower in cost. And that's sort of a huge differentiator for this alloy. So we say that it is one alloy that does it all because it is available in all forms. You can use it for wave soldering. You can use it in surface mount as a paste. It's also available in wire. It also works well with selective soldering equipment, so any type of process, REL61 can be used. It is, again, lower cost than SAC305. It tends to have slightly improved performance, which, again, many low and no silver alloys that people switch to save costs, you end up compromising on performance. With REL61, you don't, and that's sort of a real key benefit here, is you're able to both save costs and slightly improve on a lot of performance metrics. It has very good shear strength. It has, with wave soldering, really good barrel fill, really good wetting properties, lower solder pot maintenance. Tin whiskers are sometimes a concern for people. And REL61 as well as our REL22 alloy both seem to mitigate tin whisker formation. And it also has that slightly lower melting point, which is a benefit over many other lead-free alloys. This is just a comparison of some of the physical and mechanical properties of REL61 versus SAC305. Again, you see that slightly lower melting point, very similar wetting time. The hardness is greater, slightly greater thermal conductivity, similar coefficient of thermal expansion, and really good tensile strength. And this is just a rough graph of some of the cost savings. This is from 2024 data. We've actually seen cost savings percentages even higher than this, although that's highly variable depending upon the metals markets, which we know can fluctuate quite a bit. So this is a really interesting feature of REL61. In SMT applications, it has that slightly lower melting point, really good print transfer efficiency, and it doesn't degrade with thermal aging. So the pictures we see here up top, we have SAC305 and REL61, images of their microstructure when they're first cast. And then after being aged at a higher temperature, what we see is SAC305 starts to form these structures within it, and those are sort of places where cracks can occur and causes degradation of the joint. REL61, in contrast, does not form those same structures. It also works very well in wave and selective soldering applications. Of note is that there's no phosphorus added to it. Sometimes people will add phosphorus to bar solder in order to mitigate dross formation, but REL61 naturally forms less dross due to its composition, so there's no phosphorus added. One of the drawbacks of fostering, particularly in selective soldering, is it can degrade the nozzles. So that's not an issue with REL61. It also has very good performance with barrel fill. It tends to move right up the barrels in the board very well during wave soldering and fill them up. Sometimes people ask about compatibility. REL61, it's a low silver SAC is the base of it, and it has a little bit of bismuth and some grain structure refiners. So as a result, it's compatible with most elements in lead-free environments, including all other SAC alloys, nickel finishes, and trace germanium. It does contain bismuth, which means it is not compatible with lead-bearing processes, but beyond that, compatibility is generally not an issue with REL61. Next, I'm going to cover, we've done a lot of testing with this alloy. This alloy has been on the market for, I think, about a decade. And we have lots of test results, both internal and third-party testing, which proves out a lot of our internal test results as well. So the first thing we'll look at, excuse me, is intermetallic growth. So it reduces the growth of the IFC layers, which can improve solder joint durability under thermal stress. And so this is just a comparison with SAC305, tin copper nickel alloy versus REL61, and we see that slightly thinner intermetallic layer after aging at 150 Celsius for 740 hours. Here we have a wetting comparison. So this was the sessile drop test. It measures basically, you can look at the angle of contact of the drop of molten solder. Lower angle tends to indicate better wetting performance. And if we compare the angles between REL61, SAC305, and the tin copper nickel alloy, we have a lower contact angle with REL61, indicating slightly better wetting compared to the other alloys. This is just another wetting test. So here we can see on the left-hand side just what it looks like visually. We have a nice smooth surface for the REL61 samples. And then on the right-hand side, we have wetting force graphs. And what we see is that REL61 and SAC305 have almost identical wetting force graphs with improved wetting times versus the tin copper nickel alloy. This is a tensile creep test. So solder aged for 24 hours at 150 Celsius. And on the left hand, we have creep strain versus time. On the right hand side, we have the strain rate. And we're comparing SAC305 with REL61. And we see that the REL61 tends to have much better creep performance. There's a dramatic difference in these two graphs here. So the creep performance of REL61 is superior to that of SAC305 after thermal aging. This one's my favorite graph. This one shows a really significant difference in tensile strength after aging. So for each of these alloys tested, the blue bar is indicating what its tensile strength was when it's first cast. And the red bar is showing what happens after 24 hours of being aged at 150 Celsius. You'll notice that REL61 starts out high, as does SAC305, but after that thermal aging, SAC305 performance drops off quite a bit, whereas REL61 barely drops at all. And this is true across all of the other alloys as well. Many of the other alloys do not start out as high, but they also see a significant drop in performance. So REL61, again, has that really good thermal aging performance. It starts out strong and it stays strong. This is just a comparison of hardness. REL61 has about twice the hardness of SAC305 and the tin copper nickel alloy tested. This is the result of some thermal cycle testing. We have REL61 compared to SAC305, treating SAC305 as the baseline, and we looked at the performance across 3 different component types. And we see that while the performance was pretty similar for the resistor component, REL61 had superior performance across the LED component and the MLF component type. So with thermal cycle testing, we had, again, REL61 performs better than or equal to SAC305, depending upon the component. Excuse me. So with thermal shock testing, here we are looking at a resistor component. So with thermal shock, we change the temperature more rapidly. And with REL61 compared to SAC305, we see after 1,500 cycles, REL61 has no failures, whereas SAC305 is above 40% failure rate. The end result after 3,000 cycles, 60% of the REL61 joints survived, only 20% of the SAC305 joints did. So we had almost double the lifetime of an assembly compared to SAC305. This is the same test, but we're looking at different components. And again, we're seeing similar results. We have SAC305 has more of those earlier failures. REL61 at the end, only 20% had failed, whereas 46% of the SAC305 joints had. After isothermal aging for 6 months at 125 Celsius, same test performed. We have 73% failure in the SAC305 after 3,000 cycles, but only 26% for the REL61. This was a vibration test, so shake it and see if you break it. And what we see in this particular test is the performance at the end of the test is somewhat similar between the 2 alloys, with slightly lower failure rates with the REL61 in the beginning. So here the performance is more comparable, but with lower failures in the beginning for REL61. This is a drop shock test. This particular test, we have 3 different alloys being compared. So REL61, SAC305, and REL22. You might recall I mentioned at the beginning, REL22 is another alloy we have. It's considered our high reliability alloy. So it's our sort of most reliable alloy. It does not save on costs compared to SAC305, but it does outperform REL61 because it is in that high reliability category. But in this test, we also see REL61 outperforming SAC305. So REL61 outperforms SAC305 in drop shock. Both the REL61 and REL22 alloys also showed less variation in this test compared to SAC305. The tin whiskers are a concern for some people. So that's the propensity for these sort of whisker-like growths to form from a surface where there is tin. And so we conducted a test, and under the test conditions with 85% humidity, 60 degrees Celsius for 3,100 hours, we had this coated wire that we bent, and we went to see if whiskers grew off of it. With the SAC305, we can see that there is tin whisker growth in this test. With REL61, there wasn't any. REL61 also performs very well with voiding. This particular test was done using a paste with our M8 medium, and REL61 showed much lower voiding results compared to SAC305. It also does very well with print performance. Again, somewhat this is dependent on the paste medium itself as well, and not just the alloy, but we had very good transfer efficiency on fine featured devices. So this is another interesting feature. So if we take a look at what the alloy looks like after it's been melted, what we notice is it has sort of this uniform matte finish. So on the right-hand side, we see the REL61. On the left, we see the SAC305. SAC305 tends to be somewhat non-uniform in appearance with some shinier spots and some duller spots. And this matters because if you run your boards through AOI inspection, AOI inspection works by shining light on the solder joints, and that light reflects off, and the computer interprets what it sees to try to determine if the joints are good or not. And if you have a non-uniform surface that you're shining off of that has some smoother spots, some shinier spots, you can end up with interference in the data. You can end up with false calls on your AOI equipment. And then as a result, your line slows down. You have to manually inspect those joints to see if they really are problematic or not. And that has been an issue that some customers have had to deal with. But what we see, and here again, on the right-hand side, you see that nice uniform, somewhat dull appearance of REL61 compared to SAC305 on the left. And that again, makes the inspection much cleaner. We actually did a study recently with an AOI machine company, and we have some really great images sort of showing what the AOI machine sees. And here on the left-hand side, we have REL61, and you see the more color variation there is, and the more quickly colors change from one to another is an indication of how smooth the surface is. In REL61, you're getting much less of that variation. Here it is in a window pane print pattern. We see quite a significant difference between the REL61 and the SAC305. So again, what the machine is looking at is going to be much easier to interpret versus the non-uniform appearance of SAC305, which again can lead to more false calls on some of those AOI machines. This is just another AOI image from a spread test. And again, you see that stark difference between what REL61 looks like to the machine versus SAC305. Next, we're going to talk about through-hole reliability. So here we just see some images of joints, and REL61 joint is performing very well with no cracks. This was a test that was done with thermal cycling between -20 Celsius and 100 Celsius. REL61 outperformed SAC305, tin copper nickel, and a tin copper alloy in this test. This is just some of the test parameters, sample quantities, 3,000 thermal shock cycles. and samples taken at different stages. And again, REL61 outperformed the other alloys in this test. Here we see some of these joints at 0 hour. Everything looks fine across all of the alloys. After 750 cycles, we're starting to see some failures in that tin copper alloy and an SN100C. At 1500 cycles, SAC305 has failed. 2000 cycles, we still have REL61 going strong. REL61 again has very good barrel fill. It tends to flow very well, right? It has that improved wetting. Tends to outperform a lot of the low no silver alloys that are on the market. Sometimes people ask about switching their pot to REL61. If you're already using a lead-free alloy, there's no pot wash required, so it can be fairly straightforward. Another common question is how it performs with dross. And so dross is something that's highly variable. How much dross forms in a pot doesn't just depend on the alloy, it depends on all of the settings in the production process. So we performed a test under controlled conditions where we melted all of these alloys and subjected them to the exact same conditions and compared how much dross formed. And what we see is REL61 generated the least amount of dross compared to those other alloys. The only alloy that beat it was our high reliability REL22. So if dross formation is concerned, REL61 again naturally drosses less than a lot of those other alloys. So here we're going to look at some direct comparisons of REL61 with common SAC305 and some other low no silver alloys. So a lot of this is those test results I just showed you in some of the previous slides. We're looking at various metrics such as cost, hardness, thermal cycling performance, wetting, thermal shock performance, hole fill, and dross formation. And what we see when we compare REL61 with SAC305 is that it outperforms SAC305 across almost every single metric. Their tensile strength as cast was somewhat similar, but again, we saw after aging, REL61 maintained its performance, whereas SAC305 didn't. Vibration test results were somewhat similar, but across every other metric, REL61 outperformed SAC305. When we compare it to SN100C, again, we're seeing REL61 outperforming SN100C in a lot of metrics. Cost-wise, there's not much of a difference. With thermal shock and vibration, they can be somewhat similar, but when it comes to wetting performance and when it comes to that tensile strength and when it comes to dross and hole fill, REL61 in most tests ends up outperforming SN100C. SAC307 is a common choice people choose if they're trying to save costs from SAC305. It's reduced silver content. REL61 ends up being comparable on costs, but then beats SAC307 across every metric. Next, I just want to go through several case studies where customers have used REL61 in different applications and talk about some of the results they've seen and how well it performed. So in this first case, we have our M8 REL61 paste enabled a customer to reduce costs and resolve some issues with flux residues. A manufacturer had wanted to consolidate their solder paste supply, so they needed to make the case with one of their customers who was using a competitor's SAC305. They investigated the use of REL61 for the same application, and they just wanted to demonstrate to their customer that they were going to both save cost and improve performance. They had had some issues with the incumbent paste, with excessive flux residue on some of the pads and test points. So they tried out REL61, ran it on 15 panels, a total of 30 boards. And the end result was they had no issues, even without changing the reflow profile from what was already programmed in. And the residues, or sorry, the joints met IPC criteria, and the residue was minimal, and AOI inspection found no defects. The REL61 paste showed better wetting, printing, and residue compared to the competitor SAC305. So end result was they were able to demonstrate there would be cost savings because it's a lower cost alloy. Again, reduced flux residue, that was no longer an issue, and they saw improved wetting and printing performance. In another case, M8 REL61 paste performed well on a new project that had complex high thermal mass boards. Manufacturer had previous positive experience with this alloy. They wanted to obtain approval of this paste for a new product line. So they tried it out on the new application. Did require an extended profile because of the high thermal mass and high complexity of the board. So even with the extended profile, the solder joints met the IPC criteria. Only minimal brown flux residue remained, did not cause issues. Voiding was minimal, and the paste performed very well overall. And customer approved the use of the paste for development. So they saw cost savings, they saw minimal voiding, and good performance even on a complex board. In another example, we have REL61 outperforming a competitor's SAC305, resulting in reduced voiding and eliminating problems with solder balls. So a manufacturer wanted to save costs, and so they were trying out REL61 for that purpose. And they wanted to see how it compared to the competitor's SAC305 paste. They were having some performance issues that included those solder balls. In this case, they had been using SAC305 type 5 paste, and we were able to just use type 4 with the REL61. And the end results were positive, good consistent print performance. After reflow, there was evidence of good wetting, flux residue was clear, and no solder balls were detected visually or on X-ray inspection. They also reduced their voiding on both BTC and BGA components. So they saved costs, reduced their voiding, the solder ball issue went away, nice clear residue from the M8 paste. So another example, and this is a testament to that surface finish appearance that we were talking about before. They were having problems with their incumbent paste, and they were also having a lot of false calls on their AOI testing. So when they were running it through automated optical inspection, they were having to manually inspect several of those boards that were not making it through the inspection, which was slowing down the production line. So they tried out REL61 and optimized some of the other parameters in the AOI program. And the end result was better printing, better wetting, less flux residue, and much better AOI inspection results. So here's an example with a selective soldering application. So in this case, they were having poor hole fill on a bare copper, requiring they had to touch up 100% of the joints after the selective soldering, which, as you can imagine, really slows down your production line. So significant costs, significant production delays, and they needed a solution. And so they tried out the combination of our FX16 liquid flux and the REL61 alloy. And the end result was consistent 100% whole fill, excellent aesthetics on the boards, and almost no rework required in the end. So went from needing to touch up nearly every single joint to almost no touch up required, which was a huge difference for this customer. This is a wave soldering application. So REL61 combined with a no clean flux reduced dross and improved the whole fill versus a SAC307 and SN100C. So it was compared to a couple of different alloys. So they were getting a lot of dross in their wave, and they wanted to see if REL61 could help them out. They also wanted to compare SN100C as another alternative. The end result was X-ray inspection and components processed with REL61 had 100% vertical hole fill, and it provided better wetting, smoother solder joints compared to the SN100C, and dross performance. I'm not sure if it was fully quantified in this application, but they did see less dross compared to the other alternatives. So again, they saw improved wetting, 100% whole fill, smoother joints, and reduced dross by switching to REL61. This is another wave selective application. A customer was experiencing bridging and incomplete barrel fill when using SN100C. And then they were also trying to see if they could switch from using wave soldering to a selective soldering application for this board. After dialing everything in, REL61 consistently achieved 100% barrel fill and eliminated the problems with bridging. And the process was further tested with different parameters. REL61 performed well across all different settings, which also indicated a nice wide process window. So they were able to successfully transition from a wave soldering to a selective soldering application. And again, they eliminated the bridging problem, had very good hole fill, and proved a nice wide process window. So that's just some of the examples of customers that have tried this out. Again, this alloy has been on the market for, I think, at least a decade. And we've had lots of data supporting it, both in-house and third-party testing. And lots of customers have found quite a bit of success using this product. So just to summarize what REL61 is and is not. So the key thing is it is a cost-effective SAC305 alternative. So it's those who are looking to save costs from SAC305, but not sacrifice performance, REL61 does amazing in this space. So it outperforms SAC305 and it outperforms many of those other low and no silver alloys on the market. It's also very versatile. Because it is phosphorus free, it works well with selective soldering applications, not causing any nozzle degradation. And it's available in all forms, bar, wire, and paste, so it can be used across all production lines. And it is compatible with lead-free processes. So anything in a lead-free environment, including SAC alloys, it's going to generally work well with those. What it is not considered compatible with leaded alloys. Because of its small bismuth content, it's considered not ideal in that situation. It's also not classed as a high reliability alloy like REL22. So while it does outperform SAC305, It's not classified as high reliability. If you need a high reliability alloy for aerospace or automotive applications, that's where our REL22 alloy comes in as the ideal solution. This is again, our key message here. It costs less than SAC305 and performs better than SAC305. So it's a win-win, and you don't get win-wins very often. So that's a huge differentiator. This is just a summary of those physical and mechanical property comparisons. This one I had showed you earlier, the direct comparison with SAC305. Here is a comparison with SN100C. SN100C has that slightly higher melting temp compared to some of the other lead-free alloys out there. REL61 has that lower melting range, which is one of the bigger differences between these two. REL61 also has a greater hardness compared to SN100C. And again, that better tensile strength after aging. This is a comparison with SAC307. We saw in that other table that compared to SAC307, REL61 essentially outperforms across every metric except for cost. And finally, I'll leave you with just a summary of the AIM solder difference. When you work with AIM, we brand ourselves as being not just a solder supplier, but we offer support. We're solder plus support. We've been in the industry for many, many, many years. We're a global company. We have manufacturing and support all over the world. We really pride ourselves on helping our customers solve their issues. So we don't want to just sell you a product. We want to sell you a solution. We're constantly innovating. We're constantly improving our products and offering new solutions. And so we consider ourselves a great partner to work with. And that brings us to the end of the presentation portion. So I will open it up. If anyone has any questions, please ask. We have a hand raised. Felix Marty, do you want to go ahead and ask your question?
Yes, hello. Good afternoon. Thank you very much for your presentation and all these detailed explanations. Mostly we use SAC305, okay, and several times we have had some issues on the maximum operating temperature that the solder can withstand within our end product built in the vehicle. So what is the maximum temperature that REL61 can withstand? I mean, can we use it, for example, for modules that go in the engine compartment, or for zone control modules, for example, where they have to withstand engine compartment temperatures?
I think that's a difficult question to answer without knowing exact details. I can say that REL61 has that better performance with thermal cycling, thermal shock, thermal aging compared to SAC305. So my guess is you would see an improvement. There may be a question of whether you would need to consider moving to a high reliability alloy like REL22 for an application like that.
Mm-hmm.
I don't know if I have a few colleagues on the call here, if anyone has anything they'd like to add to that, but that would be my assumption.
Thank you.
Yeah, maybe you can specify what alloy is used now in that application, Felix.
Yes, SAC305.
SAC305.
Yeah.
So I would assume that
Type 3 and Type 4. Yes.
Mm-hmm. I assume that if SAC305 works, then REL61 should also work. So there should not be limited. And what are the limit temperatures there? The maximum.
It was more than 125, around 130 degrees C that our product was seeing. I think it was around this temperature. I'm asking the question because usually with the lower silver content, the material, the temperature, the highest temperature it can withstand is a bit lower because the silver gives a high temperature, let's say, performance. This is why I was asking, since we have less silver on this alloy, right?
Yes.
Okay.
Yeah, that might be something you'd need to conduct, just conduct testing to compare. Yeah, without directly testing the alloys, it's hard to guess ahead of time.
Yeah.
But what we do know is that REL61 does outperform SAC305 with a lot of thermal cycling and
Thermal
thermal
cycling.
aging performance. Yeah.
Okay. Thanks. Thank you very much. I believe you have all different types, right? Type 3, type 4, type 5. With
Yes.
okay.
Yep.
Thank you. Thank you very much.
Any other questions? Well, I will add that we will be sharing a PDF version of this slide deck with everyone here, so you guys will be able to reference those slides. And again, if you have any additional questions after this webinar, you can definitely follow up, either sending an email or with your AIM Solder technical support person. So before we conclude, open it up for any more questions, or if any of my colleagues have anything they'd like to add before we conclude? All right. All right, well, we'll wrap this up. I again want to thank everyone for coming. I really hope you did find this informative, and definitely let us know if you want to follow up, if you want to try a sample of REL61, and see how it works for your process. Thank you, everybody.
Thank you. Thank you very much, Gail.
Thank you very much. Thank you.
Thank you.
Thank you. Thank you. Bye. Thank you. Goodbye.